This problem is from the 2016 Sir Isaac Newton Physics Contest. The essence of this problem is simple. We have two objects, one of mass 1 equals 4 kilograms, connected via a spring to another mass that's slightly larger with a mass of 6 kilograms. Now we're going to drop these two objects from rest, and we want to figure out when these two objects will first collide. Now, before we begin, I would like to mention that gravity really doesn't do anything in this problem. Yes, it's pulling them down, but it's pulling them down both at the same rate, and therefore their relative accelerations wouldn't really change. It's similar to how a spring attached to the ceiling versus lying on the ground, horizontal surface, would have the same period of oscillations. So we can just imagine these two objects as oscillating back and forth on a horizontal flat table. We can sort of draw out the diagrams to see what would happen. First, what we're worried about is when they first collide. And when they first collide, these bodies will look something like this. And the orange ball, the slightly heavier one, would be going up. Afterwards, they'll reach their maximum stretch and they would switch places. And finally, they would go back to before, such as similar to the second case, but the orange ball would be going down. And finally, it would reverse and go back to the original situation, where the orange ball is at the bottom. Now, this represents the motions for a simple harmonic motion. And we know that the period for simple harmonic motion is equal to 2 pi square root mass of the object over the spring constant k. Since this is divided into 4 steps, each step would be 1/4 of the total period. So we might be tempted to say that the period or the time it takes for us to get from step 1 to step 2 is 1/4 of this period that we found here, or 2 pi over 4, the square root of m over k. But what value of m should we use? Should we use 4 kilograms, 6 kilograms, or 4 plus 6 kilograms? The answer is none of them. Remember, this formula only works when there is one mass attached. And there are two masses attached to this. And we can't just add these two together because they will have countering impacts on the acceleration of the system. For example, that would only work if both masses were at the bottom or both masses were at the top. Since they're at opposite ends, the effects would be super weird and we wouldn't really have a definite understanding of how it behaves. However, there is a trick, and it's something called the reduced mass. Now, this expression comes up a lot of times during two-body problems, such as if you have an Atwood's machine, if you have two objects orbiting each other, or two objects connected to a spring, or even an electron orbiting a proton. You have a quantity called the reduced mass, or I'll just call it mr, and it's going to be equal to m1, m2 of m1 plus m2. What you can do in these cases is you're able to take two masses and combine them together such that they have the same effects as if there were two masses, even if they were at different places. And it's given by this quantity here, and unfortunately I will not be deriving this in this video, but if you search up reduced mass on Wikipedia, it does provide a neat derivation that's not too hard to understand. So we can really imagine this as a spring with a reduced mass, mr, of m1 times m2 over m1 plus m2. So we can write out the time for the collision as 2 pi over 4, or pi over 2, the square root of the reduced mass, or m1, m2, over m1 plus m2, times the spring constant k. We can substitute values in, and we get pi over 2. M1 is 4 kilograms, M2 is 6 kilograms, their combined mass is 10 kilograms, and the spring constant would be 10 as well. So we get, if we do the math and plug into a calculator, we should get something around 0.769, which is the answer here. The answer is A. Yay! Now this provides a really quick solution, and if you're familiar with reduced mass and how this resembles a simple harmonic motion problem, you should be able to solve this problem in what? Less than 2 minutes. However, if you don't know about reduced mass, as it's something that's not typically taught or taught so that you could apply it in a real problem setting, there is another way to look at it. And it comes with one of the most favorite techniques that the Sir Isaac Newton Physics Contest creators like to use, and it's called the center of mass. So recall that if this is our two objects, and I'll draw the orange M2 as slightly bigger, there are no external forces acting on this system. Sure, there's a spring force acting this way for the object, but there's an equal and opposite force, the spring force, acting the opposite way from the orange ball, and these two forces would cancel. There are no external forces giving this system, enclosed within these dotted lines, an acceleration. So therefore the center of mass of this system would stay the same. Since the center of mass of this system is somewhere towards the right here, leaning towards the orange mass, we're going to say this value is the center of mass. And just for simplicity's sake, we'll say that the total length of this spring initially is L. Now, what we're going to do is we're going to calculate what the center of mass actually is. Recall from physics that the center of mass of two objects is given by m1 x1 plus m2 x2 over m1 plus m2. Now we need to set where our 0 is. We can really set our 0 anywhere, but to make it more official, like easy, we'll set it over here. The reason I set it over here as x equals 0 is that when we're talking about the center of mass, or the location of the center of mass, it makes a lot more sense to us, and we can draw a definite analogy so we can use our intuition. But really, any point that you choose is fine. And I also chose this point because if you sub in x1 equals 0, we get a simplified expression. So we have m1, and the location of m1 is 0, so that would become 0 eventually. We have m2, and the location of m2 is just L. And we can divide that all over m1 plus m2, and we'll get m2L over m1 plus m2. Now notice that the length of this spring doesn't really matter. No matter how far away the spring is, the time for the oscillations would still be the same. You can draw an analogy with regular simple harmonic motion where the amplitude doesn't affect the period of oscillations. So we can set L to be any convenient number, and I feel like setting L to be equal to 1 meter, just to make it convenient. So let's set L equal to 1 meter, and we get m2 over m1 plus m2. So that would give us the location of the center of mass. Now let's just make it easier on ourselves by substituting in some actual values. M2 would be 6 kilograms. M1 plus M2 would be 10 kilograms. So that would be equal to 0.6 meters. So what we can basically do is treat this problem as a problem with two springs. We have a spring attaching the first object to this anchor, which is our center of mass, and we have another spring attaching our larger object also to this anchor. Now, because of having two separate springs, we now go back. Are now able to go back to the problem which we are familiar with, which is a spring connected to one object. And since this pivot point doesn't move any time in the system at all, we can say that this point is stationary and that we can really disregard the effects of the other half of the problem. So we can ignore completely what's happening for all the orange bits. Or we can say that we only care about the orange bits and we completely disregard the black part. Both of these are perfectly valid because the time it takes for both the black and orange mass to come to the center of mass would be exactly the same. So let's ignore the orange mass here. Oops, I'm running out of space. But I think we have enough. Now, we need to do one last thing because the spring constant of this spring right here, just the black spring, is not going to be equal to the spring constant of the total spring together. However, since we're just rephrasing this problem, the only thing that's going to really change for us, is the spring constant and the length, but all other physical quantities is going to be the same. For example, the force this black object feels will be the same. So let's calculate what the force it feels at the very start. So we can say that the force it feels, if we treat it as a total spring, is equal to kx, where k is equal to 10 and x is going to be equal to 1 meter long, so it's going to feel 10 newtons of force. Since we're just rephrasing this problem, it will still feel a force of 10 newtons. But since the length decreases, that means the spring constant must increase. So we have 10 newtons is equal to, the length, remember, is 0.6 meters. We have 0.6 times our spring constant. And if we divide both sides by 0.6, we'll get k is equal to 16.66. And again, now we just have, I'll do it on this side. Now we just have a spring connected to one mass, and we want to figure out how long it takes for it to complete 1/4 of a revolution. What we're going to be doing is we'll just say that the time would be 1/4 of a revolution, so 2 pi over 4, the square root of the mass, which is going to be 4 kilograms, over the spring constant, 16.66. And if we calculate that, we'll get the same answer of 0.769 seconds, which we can see here is A. So 2 different methods, both easier than the one given in the official solution, for you to calculate the time it takes for 2 objects to collide in a simple harmonic motion. Thank you.